Okay, let's dig into life science. We're going to start with Unit 1, Chapter 1. Let's go ahead and just click on the book, and we're going to be looking at ecosystem interactions. And we're starting with Earth's spheres. So um, it makes sense then that we're probably going to be talking about how those different spheres interact. All right, so go ahead and click on Concept 1.1, Earth spheres. And we'll jump right into our Explore. And let's go ahead and just turn that off there. Okay, the essential question: what are the major components of the Earth system? Go ahead and write down what you know, what you think. Okay, hopefully you hit pause there and took care of that. So, Roman numeral 1, many spheres. Hopefully, this is a review for you. And as you're thinking about it, you're thinking about, of course, the geosphere, the land, the hydrosphere, which includes all the water on the planet. Um, by the way, make sure you kind of internalize in your brain geosphere is both the exterior, the stuff that you and I are standing on, but it's also the interior of the planet. Okay, and when we talk about the hydrosphere, some things jump right out at us. You think about oceans and rivers and lakes, of course. Maybe you thought about ice, right? You think about Antarctica and the Arctic. That's part of the hydrosphere. And maybe if you're very astute, you may have thought about the water vapor in the atmosphere. That too is part of the hydrosphere. Okay, that brings us to the third sphere, the atmosphere, all the air surrounding Earth, and the biosphere, all the life that's found on Earth. Like we said, all spheres are interdependent, they support each other. Um, Notice in purple here, energy and mass move among the spheres in an attempt to establish and maintain states of equilibrium. That's a very important statement. I want you to focus on that. Okay, the energy movement and the movement of mass. Okay, so energy is distributed around Earth continuously. How so? When heat is transferred, right? The solar energy from the sun heats up the surface, both land and water. It drives evaporation. It drives the warming of the surface, which warms up the air, which causes air circulation to happen. So the common phenomena we see every day is related to this energy that's being cycled. Okay, and you can see there we got different circulation systems: the water, the air, convection currents in Earth's interior, not directly related to the sun, but still they help drive things. Okay, so let's take a look at the geosphere. This is hopefully familiar. You can see the basic diagram, including a core, which can be divided into an inner solid core and an outer liquid core. You can go to the next layer out, which is the mantle. And the mantle can be broken down basically based on its rheological or structural features. There's the mesosphere, the asthenosphere, and there's the upper mantle. And then you have the crust. And if you recall, the crust has a continental and oceanic. The oceanic is the denser of the two crusts. And if you recall that word lithosphere, the lithosphere is the crust and the upper mantle together. And that's what we refer to when we talk about tectonic plate movement, right? Those broken, fragmented plates that are moving all the time. So the geosphere is dominated by 8 elements. In your text, you can go ahead and refer to that to see all of them. I went ahead and just gave you the top 3. Oxygen is 46% of the geosphere. Surprising, maybe. Aluminum is the second most prevalent at 8%, and iron is 5%. Okay. If you were a miner and you were to work in some of the deepest mines in the world, which are about 3.5 kilometers deep or kilometers deep, you would notice as you descended into Earth that it got warmer. In fact, it gets 25 degrees Celsius warmer for every kilometer you go down. So if our deepest mines are 3.5 kilometers, you're talking about 150, 160 degrees down there. Pretty warm, right? That's called your geothermal gradient, by the way. This idea that it gets warmer as you go deeper into Earth's interior. Okay, you will hit a point where it doesn't get any warmer, and that's when you get to the core, about 5,000 degrees Celsius, which is about the temperature of the surface of the sun. May be like, oh, wow, we're as hot as the surface of the sun. No, the core of the sun is really quite hot, millions of degrees Celsius, all right? All right, so the hydrosphere. 70% of Earth's surface is covered with water. 97% of the water on Earth is found in the oceans. The remaining 3% is found in everything from ice to groundwater to lakes and vapor. We'll look into that a little deeper in a minute. Water classification is based on how salty or how many dissolved solids you find in it. So here's your breakdown. You have your fresh water, which has low concentrations, less than 0.5 parts per thousand. And then you have your salt water. And salt water can be broken into your brackish water. Think about maybe if you were in Florida and the salt water was mixing with the fresh water, we call that your brackish water, 0.5 to 30 parts per thousand. Salt water in general is 30 to 50,000 parts per thousand. Remember, that really depends on how deep the ocean is, how warm it is. If you're in really warm areas, there's a lot of evaporation that leaves a lot more salt in the water. If you have a shallow sea, say like the Red Sea versus a deep sea, that's going to affect the salinity as well. And then you have brine water, which is the most extreme at 50 parts per thousand. Okay, now the cryosphere. Cryosphere is all frozen water. Typically, you should be thinking glaciers, which are those moving ice sheets on land. Ice shelves, those are glaciers that have moved off the land onto the water. Sea ice, frozen ocean water. You see the trade routes, the Russians and whoever is trading and having to move cargo in the very cold oceans. They have icebreakers to break up the sea ice. You have permafrost. This is land that's just permanently frozen. Think the tundra, think the Arctic, think maybe parts of Canada, Alaska. Okay, so saltwater. Let's break saltwater down a little bit more here. Interesting. Almost every element in the periodic table can be found in saltwater. Maybe not to the same level, same concentrations, though. In fact, you have some that we call your major constituents. There's about 6 of those. I just gave you the top 2, chloride and sodium. That makes sense, right? Salt. Refer to your text for the other ones. You have your minor constituents, dissolved salts ranging from 1 to 1,000 parts per million. These are ions that tend to leave the ocean faster than they enter the ocean. And then you have your trace ions. And these are even found in smaller concentrations, 1 part per million. They often get used up very quickly through biological processes, that's living organisms, and through chemical reactions. Okay. All right. So we've got fresh water now. Remember we said that 97% of the surface water is found in the ocean. 3% of the planet's surface water is fresh. Now, look at this. 69% of that is trapped as ice. 30% is underground. That means only 1% of that 3% is actually on the surface as lakes and rivers. Really not a whole lot, is there? In your text, it's going to go ahead and take a look at things like water flow. And I should be trying to move this along with us here. So let me just scoot this down so that we're kind of tracking here, okay? Okay, here we are. So, in general, your text examines how water flows, often from headwaters to streams to rivers, and then from rivers, they often can enter into larger reservoirs such as lakes, bays, seas, and oceans. Your text makes a point to talk about changes that occur to water as it flows. Temperature may, in fact, increase. Think about headwaters that maybe are high in the mountains. Maybe there's snow, melt, cold water, but as it descends, it starts to warm up. Oxygen levels may decrease. And that has to do with these becoming slow, sleepy rivers, less oxygen, more plants, more dead material that accumulates in there. When you're up high near the headwaters, you have a lot of waterfalls, you get a lot of aeration, so a lot of oxygen. So the oxygen levels decrease as you proceed down downstream. And then clarity also decreases. The water goes from being nice and crystal clear to often dirty, right? A lot of sediment flowing in there and a lot of biomass, algae, right? Okay. Now they're also going to go and talk about groundwater and your water tables. So you can see that at the very top here, you have your sediment, you have your soil, and it rains. The rain is going to soak through that soil. It's going to enter into what's called an unsaturated zone. This is, you dig your shovel and you're not going to just hit water right away. That's your unsaturated zone. Below the unsaturated zone, you're going to hit, and this is where also water can pass through your aquifer, where you start to get into porous rock material. Eventually, you're going to hit what we call the water table. This is where the saturated zone, the seasonally saturated zone, is encountered. That means that when it's raining, that zone will be saturated, but in the summertime, it's not. All the way down to the saturated zone. Those two together are going to make up your water table. Okay. Roman numeral 4, we start to talk about the atmosphere. Your text makes a point to talk about it being like an ocean of air, an ocean of mixed gases. And that's appropriate in some ways because we often talk about the fluid behavior of air. It flows like liquids. So it is a mixture of gases. Nitrogen is the most prevalent. Now, these numbers do change as time goes on, but right now, 78% of the air you're breathing right now is nitrogen, and 21% of it is oxygen. That leaves just a what is that, 78, 88, 98, 99. That just leaves 1% to be divided amongst the various greenhouse gases and other trace gases. Volcanoes have historically been a source of many of our gases. More recently, the oxygen you're breathing is a product of photosynthesis. Okay. If you take a look there, we've got the various greenhouse gases listed: carbon dioxide, water, methane, sulfur dioxide, ozone, nitrogen oxides. Obviously, these are relatively small in concentrations compared to nitrogen and oxygen, but they do play an outsized role in their effect on the planet. What happens is the sun's solar energy heats up the planet. As Earth warms up, it emits long wave radiation, and these greenhouse gases are really efficient at preventing that radiation from exiting back to space. And so it gets trapped, and that starts to increase the temperatures here on the planet. Most particularly, we see that absorption in the oceans, and it's remember, water has a very high specific heat, so it can absorb massive amounts of energy, and it barely goes up in temperature, but it's its effects are tremendous, and to lower those temperatures will take a very long time because water is also very efficient at holding on to heat. So, more on that. Now, here's something that is interesting. Are greenhouse gases all bad? Not necessarily. If we did not have some level of greenhouse gas, Earth would be very cold, right? The energy that uh, from the sun heating up the surface would leave at nighttime. Every 24 hours, we would dip into temperatures that would kill life. So it is good that we have some level of greenhouse gases. It seems like we've got to really walk that fine line of knowing how much is the right amount. Now we're moving into the biosphere, bio meaning life. So we're talking about all parts where life exists. You'll notice that it's kind of defined as this zone 9 kilometers above Earth's surface. So we find all kinds of organisms that are living up in the air, from plants to various airborne bacteria and spores that can be encountered, right? All the way down to 11 kilometers beneath the ocean floor you can find organisms. So that zone there, okay? So why do you find life just in this narrow band? Two really important factors, and this is what we look for when we look for other planets that humans could move to and colonize if Earth ever had a problem. Is there liquid water? You need water to be in a liquid form. And is there energy flow? Right? Because just like here on Earth, we have to have that energy flow. We have to have that heat flowing through our systems to drive these cycles. Okay. Interestingly enough, this energy flow that starts with the atmosphere letting the sun's energy enter keeps us at about 59 degrees Fahrenheit. Okay. Taking a look at A and B, when we talk about Earth, we talk about it. In terms of energy, we say the Earth is an open system. We tend to gain, we tend to lose energy. When we talk about matter, right, you think about carbon cycles and nitrogen cycles and that kind of stuff. We tend to talk about them in closed systems, like you can account for all of the different matter. It's a closed system. It's just kind of some loose ways that that Earth is referred to there. Last, the magnetosphere. That wasn't necessarily part of our initial listing, but your text goes ahead and throws it in there. Remember that the magnetic field is generated from the core. You have a solid iron core, iron, nickel, magnesium core, spinning in an outer liquid core. Why is it turning and spinning? Because the Earth is rotating. This produces something of a small engine kind of effect, a motor, a magnetic field is generated here. And that interacts with the solar particles, the ions that we call solar winds that are coming from the sun. And in fact, they're protecting you and myself and all of life. If we didn't have that magnetosphere, and the magnetosphere is what we call that magnetic field interacting with those charged particles. If we didn't have that, our atmosphere would be ripped apart and life would not be able to be sustained. Okay, so you can see a little schematic here. Your text also goes and refers to the Van Allen belts, which is a small amount of this ionized energy coming from the sun that actually gets trapped in our gravitational fields, about I think they said 6 kilometers up high. Let's see if we can find that in our text there. About 6,400 kilometers above Earth's surface. That's a big difference, huh? Okay, well, that was a whirlwind tour. So take a moment and make sure you got all your notes and then write yourself a summary paragraph. And we'll talk more about this in class.